he's going to consist of chapter 7, 8, and 9. We're not going to put any chapter 10 material on it. Just 7, 8, and 9. Wednesday's holiday, correct?
Yes.
Yeah, okay. What I'm going to do for this test is it's going to be mainly multiple choice. You should know how to draw. If you're going to draw something, or let's see, calculations. Were there many? Yeah, there are calculations in this chapter.
When you say chapter 7, do you mean like in the part we stopped at chapter 7? Do you mean we stopped at first one?
Well, yeah, there's a part we stop at, but the part we stopped at, officially it's going to be after the part we stopped at.
Yeah.
But the problem is the stuff after the part we stopped at, you still need some of the earlier stuff, and so the focus will be the latter stuff, but you still need to know how to do certain things like Q calculations and that type of stuff, and so that's why I just say chapter 7. Comparable. But I'm not going to ask you things like specific heat, those types of things. Yeah. The equations will be given, but yeah, just the basic standard equations. If you don't see equation, ask me. Right.
And on the practice exam, I follow some chapter 6 stuff, like ideal gases and stuff?
No. None.
Okay.
No ideal gas. I think that test I forgot to cover something earlier. All right, other questions? So mainly multiple choice. The way I can grade it quickly. You need to be able to draw certain things. I always ask this every semester, is to draw the energy level diagram for a multi-electron atom. But a lot of mistakes. Like for example, the ordering of the orbitals. Sometimes they don't clearly show. So 4s and then 3D is higher in energy. A lot of people end up putting 3D lower in energy or the same energy. Getting that wrong. Also, people forget how many orbitals there are. So they don't write enough lines. Some people just write one line for each orbital. Like 4s has one line, and 4p has one line, and 3d has one line. I'm not, necessarily expecting those mistakes this semester, but let me just warn you in advance. I want an energy level diagram, and every semester somebody asks me, what is an energy level diagram, during the test, but I'm not gonna tell them, because a lot of people end up writing this. Is this an energy level diagram? No, that's not what I want. If I'm gonna give you a lot of space to write something, then you wanna give me as much information. Yeah, orbital box diagram, orbital diagram. It's very compact and it's nice, and all the homework is like this, and so people think on the test they'll just have to do it like this. But no, I want, I want this one where you have the 1s, the 2s, 2p, etc. Okay, how high up do you need to memorize this till? 4p. 4p. All orbitals including the 4p. Okay. So be able to draw that. Okay, then you'll have to write the quantum numbers. Can you write all the quantum numbers for all the orbitals? If I say label the orbitals with quantum numbers and the ns, whatever, 1s, 2s, but you'll also have to do this. And so this is what I mean by label the orbitals. Label it 1s, 100. You don't have to label it like this, psi 100. You just eliminate the psi. So can you do that? And then also filling these orbitals with electrons. And can you determine the quantum number for any particular electron between 1s and
How many
14?
guys are like plus 1/2, like 1, 0, 0, plus 1/2?
You just tack it on in the end. So, you know, this would be 1, 0, 0 plus 1/2. Just 1, 0, 0 minus 1/2. The way we read it is NLMS. NLMS. In a series. And so those would be the 4 quantum numbers. And so, also, you know, you should be able to draw the basic shapes of the orbital, like an s orbital, electron cloud like this, or 90% boundary, 1s orbital. And then a p orbital, you know, p orbital would be something like this, you know, kind of thing. Or at least recognize, you know, d orbital. What does a d orbital look like? Yeah, 4-leaf clover.
With 1, 0, 0, that should yours label be the NL and MS, right?
Yeah.
It's not 100. It's just 1, 0.
1, 0, 0.
Okay,
That's it. Yeah, you don't. You wouldn't call it 100.
Okay.
Yeah.
And then you tag on the spin by just putting plus.
Yeah, plus or minus 1/2.
Okay.
That's it. And so you'd have to know all those. For the most part, I'm going to give you the equations, but there's some equations I'm not going to give you. For example, I'm not going to say that there's n squared orbitals for each n, or that, you know, there are 2l plus 1 orbitals in each sublevel. You know, these patterns, I mean, you could just generate the table and figure it out for the most part. But those types of equations, I'm not going to give. The equations I will give will be the thermodynamic and equations in the R, you know, that kind of thing. What else do we have?
Lewis structure.
No Lewis structures on this test. On the practice, did I ask you to draw Lewis structures?
No.
No, okay, no Lewis structures. Multiple choice type questions would be like, which atom's bigger? You know, oxygen or nitrogen, you know, something like that. That's for chapter 9. Chapter 7, you'll just have calculations, you know, but multiple choice. And conceptual things. Chapter 7, probably a lot of conceptual things, you know, about delta U, delta H, like the practice test. All right, any questions about the test? Any other questions? Uh-huh.
I got a question on that, right? When you say label the diagrams, you basically mean.
Yeah, you put like maybe an energy arrow like this or something like that. And then when I say label, I mean this. A 2s is a 200, right? And then 2p, this is 2, 1, you know, negative 1, 2, 1, 0, 2, 1, something like that.
I think questions about chapter 7. There's weird questions like, there's just a solid, you know, bomb. Found under there's no gas at all, and then the gas forms.
Mm-hmm.
Was that a change in volume?
Mm-hmm.
Just so even though there was nothing in there, now there is gas. It's not a change.
Oh, you're saying there's.
There's one reaction in the homework that was like just a solid, with 0 moles of gas on one side, the product there was a mole of gas. It's in a bomb.
I see what you're saying, because you're saying that the. Well, the problem is when they say there's no gas in there, what does that mean? If there's really no gas in there, what that means is it's a perfect vacuum. To get a perfect vacuum in a bomb, you'd have to have extremely powerful pumps. In fact, it's impossible. You can't generate a perfect vacuum on Earth. It's just too difficult because you're always going to have vacuum leaks. Even through the steel, let's say there's no leaks at the joint, even through the stainless, and you could use heavy-walled stainless steel, you're going to get gas molecules that can diffuse in there, like, you know, especially some lighter ones. And so when they're saying no gas, it's just air that's in there.
Okay.
Okay. Otherwise, this would be tremendously difficult. Other questions? Which lab are we doing tomorrow? Same one? Experiments 8 and 9? Okay. Yeah, just try to work on the Lewis structures. We're going to continue with Lewis structures for that. Tomorrow I'm going to do some more talking about chapter 10 and 11. Caught up. Let's do a chapter 10. One of the periodic trends that we see is something with the melting point. Now, if we look at the melting points for, let's just go with boron, carbon. What carbon has? Actually, let's not do this. Let's do the next row. Let's do aluminum, silicon, phosphorus. So we'll go about this: sodium, magnesium, aluminum, silicon, phosphorus, because we have some data for this. Sulfur, chlorine, argon. What they mean by a periodic trend is there's some kind of pattern to this, and this pattern repeats itself. So if we look at, the period above it, lithium to neon, or the period below it, potassium to krypton, we see the same kind of pattern. And the same kind of pattern is like this. When we look at the melting point, do you know what the melting points are going to look like? Something like this. What do you think is the highest? What do you think has the lowest melting point? Well, I think so. Actually, out of all these, argon and chlorine, because argon and chlorine are both gases. And then I think like sodium, magnesium. Sodium and magnesium, they don't have that high of melting points. They're pretty easy to melt. Same thing with aluminum. Sulfur is pretty easy to melt. 100 degrees C will melt yellow sulfur. But when we get to phosphorus and silicon, those are going to have much higher melting points. And so the pattern of the melting points looks like this. Peaks. Silicon has an extremely high melting point. Very hard to melt this stuff. Actually, this just skyrockets up here. So we see a peak here, melting point. Something like this. And so what makes something hard or difficult to melt? What makes something difficult to melt are the bonds. The stronger the bonds or the stronger the intermolecular force is, the harder it is to break it apart, to melt it. And so this just tells me silicon has the strongest bond. Silicon's melting point is like over 1,000. It's really hard to melt. And so one of the things what we see is, okay, so this has got to have the strongest bonds, right? Strongest bond. All right, and what we have here is we have one valence electrons, 2, 3, 4, 5, 6, 7, 8. And so there's something about the valence electrons that we have. And so if we're looking at this shell is, for silicon, this shell is half filled, the entire shell. And so that has some significance because when we have something like that, then we can maximize bonding. What we say is that silicon is capable of forming 4 bonds because when we look at this shell, this is the way we write it. Silicon has 4 electrons in the valence shell. And Although, you know, 2 of the electrons in 2s, so we're going to split those apart. We're going to split those apart because that's what happens. The electrons get separated because if we separate the electrons, and it doesn't cost too much energy, what we get in return is we can form more bonds. And so if we left the, not 2s, 3s. Silicon has 2 electrons in 3s and 2 electrons in 3p. The 2 electrons in 3p are separate naturally, but let's just write this out. Silicon would be, what would it be, neon? It would be neon 3s2, 3p2. And so when we look at the energy level diagram looks like this. So 3s with 2 electrons here, and 3p with 2 electrons here. And what happens is, because of bonding, you know, why do bonds form? Bonds form because you're going to form something more stable. And so because of bonding, you know, bonding gives a lot of energy in return and stability. And so what we can do, and we've seen this before, happen before, but we promote an electron up here. By promoting an electron up here, what can happen now is we can form, rather than forming 2 bonds, we can form 4 bonds. So we'll split it up. And so this is our 4 valence electrons here. 4 valence electrons are shown here. And so silicon has a very high melting point. What would you think about carbon? Same thing. Carbon has an extremely high melting point. If you think about graphite, you know, graphite, it's too hard to melt. Usually what happens is graphite starts to sublime, vaporize, rather than melt. You know? The same thing with diamond. Have you ever tried to melt a diamond? Have you heard of anybody melting a diamond? No, it's too hard. It's because of the bonding. Not just one specific bond, but the maximum bonding, because something like phosphorus, you know, phosphorus can form 3 bonds, you know, sulfur 2 bonds, chlorine 1 bond, argon no bonds. You know, same thing, aluminum with 3 bonds, if you're looking at a molecular compound. Magnesium and sodium form metallic bonds. So those are weak. Okay, so we want to form bonds, and then what kinds of bonds can we form? So let's take a look, because we see a difference in bonding here. Look at it. Well, first we're going to look at covalent and ionic bonds. We're going to look at metallic bonds. We'll look at a little bit later. So, the first thing is something like sodium and chlorine. So sodium has 1 valence electron. Chlorine has 7 valence electrons. Chlorine's a powerful oxidizer. Sodium's a good reducer, and so we can have a redox reaction occur. So what's going to happen is this chlorine's going to just pull off this electron here to form sodium chloride. When sodium chloride forms, sodium's left with no valence electrons and a positive charge. For loose structures, we always write brackets and show the net charge on the outside. Chlorine's going to have 8 valence electrons, and the net charge is -1. This is an ionic bond here. Ionic bond. And sodium chloride has a very high melting point, like 700 degrees C. It's because these ionic bonds are strong, but really what we generate is something called an ionic lattice, you know, which happens for salts, like sodium chloride. In the ionic lattice, we have sodium ions and then chloride ions. Which one is bigger, you know, sodiums or chlorides? Chlorides are bigger, a lot bigger. And you just think of these as positive and negative balls. So each positive ball wants to surround itself with as many negatives as possible. And each positive wants, each negative wants to surround itself with as many positives as possible. When we do that, we generate the ionic lattice. And so when we're breaking up or melting sodium chloride, we're not just breaking one bond, but we're breaking what we call a lattice of bonds. Lattice of bonds. And so if I have a mole, if I want to melt 1 mole of sodium chloride, I'd have to break 1 mole of ionic bonds? No. In 1 mole of sodium chloride, there are just a huge number of bonds. Because for each sodium ion, I'm going to have 4 ionic bonds in the plane, and then there's a chloride sticking on top and a chloride sticking on the bottom. For each sodium, I have 6 ionic bonds I have to break with the nearest neighbor. The same thing, for each chloride, I have 6 ionic bonds with the nearest neighbor. But it goes beyond that because, the next nearest neighbor, it's going to be a repulsion, so that helps weaken it. But the next nearest neighbor is an attraction. And so every other neighbor is an attraction and a bond. Although Coulomb's law says the strength drops off dramatically. But anyway, this is what we can have here. We have an ionic compound, ionic bond. If we have hydrogen, the ionization energy for sodium is less than 500. That's around 500 kilojoules per mole. It's the ionization energy. But for hydrogen, what is the ionization energy, roughly? For hydrogen, the ionization energy is roughly 1,500 kilojoules per mole. And so it's 3 times harder to ionize hydrogen than it is sodium. So sodium is a much better reducing agent because it's a lot easier to ionize. Hydrogen is not as good, right? And so what happens with chlorine is going to have a bit more of a struggle to try to oxidize hydrogen. And so chlorine comes in here and tries to oxidize hydrogen, take that electron, but it's not going to be completely successful. And so what's going to happen is we're going to form a covalent bond in hydrogen. This is the hydrogen chloride molecule. Now, if I take that in water, water can break it apart into the ions, or water can ionize it. But what we see is something like this. The way we're going to represent that is by an electron cloud. And so here, these 2 electrons went entirely to the chlorine. It's a lone pair. However, this one, chlorine is stronger in this tug of war for electrons, but chlorine isn't as weak as sodium. And chlorine isn't strong enough to pull the electron off completely. And so what we form is a polar covalent bond here. Polar covalent bond. There's some sharing because hydrogen hasn't completely let go of the electron. This is a molecular compound. We can form polar covalent bonds in molecular compounds. We can also form covalent, polar covalent bonds in what we call network covalent lattices. And so an example of that would be a quartz. Quartz is this lattice of silicon and oxygens. But it's not an ionic lattice. It's a covalent lattice. It's a network covalent lattice. So something like HCl has a very low melting point. It's a very low melting point because what holds two HCl molecules together are dipole and dispersion forces, just intermolecular forces. But when we're looking at this, oops, I forgot an oxygen here. Sorry. It should not be a silicon-silicon bond. And these are all polar covalent. Silicon is weaker, than oxygen. Oxygen is stronger. So we form polar covalent bonds here. So we get this lattice of polar covalent bonds. This would be quartz. Like quartz crystal. And so what's the melting point difference between these is huge. You know, quartz crystal is the quartz crystal obviously is very hard to melt. Over 1,000 degrees C to melt it. You can melt it though. People melt it all the time. Sand, it's basically sand. Make glass out of it. And so there's a quartz. If we take two chlorines will react with each other. These are atomic chlorines. You know, each chlorine is going to try to oxidize the other. This chlorine is going to try to take this electron, this chlorine is going to try to take that electron. It won't be successful. And so in this case, we end up with a non-polar covalent bond. Non-polar covalent bond, the electron cloud is going to be symmetrically distributed between the two atoms. Here, this would be a molecular species. I hesitate to call it a compound because usually compounds are two or more elements, that are different. But this would be an element, so it's a molecular element. And of course, we can also have a network covalent lattice that's nonpolar. So for example, diamond is nonpolar. Diamond, interestingly, has the same structure as quartz, except it's all carbon atoms. And well, not exactly the same, but it's similar in certain respects. This is not, a crystal is usually very well ordered. This drawing is not very well ordered. This would be like diamond, which is network covalent. All the bonds in diamond are nonpolar. Diamond itself is nonpolar. All right, and so what we see here is this. We go from nonpolar to increasingly polar. And so we call it the polarity. Ionic bonds are the most polar. They're so polar they form dipoles. Dipoles will have two poles, a negative pole and a positive pole. But we also have dipoles form in polar covalent bonds. But the difference between these dipoles, the dipole of sodium and chloride, and the dipole of HCl, is that sodium chloride involves full charges, positive and negative, whereas HCl involves partial charges. For partial charges, we use the delta symbol. Partially negative here for chlorine, and partially positive here for hydrogen. There's no dipole here. Both are zero, neutral. So increasingly polar. All right, now, when does it get polar enough that we can call it, you know, ionic? You know, there's some kind of cutoff here. These cutoffs are somewhat arbitrary. And what we're going to do is we're going to look at the strength. We're not going to look at the numbers because, you know, we can tell you a lot about, you know, its attraction for electron is its ionization energy. You know, the easier it is to ionize, the lower the ionization energy, the more likely it is to give up an electron. The higher the ionization energy, it doesn't want to get rid of any electrons. The higher the ionization energy, that means Z effective is very big. You have a very big Z effective, then it has the ability to attract other electrons. And so things like chlorine. So we could use ionization energy to kind of figure out, you know, the difference in ionization energy, but there's something else that's related to it. And something else that's related to is electronegativity. And what does electronegativity stand for? Electronegativity stands for just the ability to attract an electron. How does electronegativity differ from electron affinity? Well, electron affinity is the ability to attract and to hold an electron. And so what we can do is we can use electronegativity as a guide. And so electronegativity. And the way we can read electronegativity is it's a tug of war. If you're having a tug of war for electrons, the species with the highest electronegativity will be the strongest. And so what we want to do is we look at this. We look at if there's atom A and atom B, then we look at is delta En, the difference in electronegativity. You know, between A and B. We usually just do positive, you know, this absolute value. Just looking at it. All right, the species with the highest electronegativity is going to be something like fluorine, which has a 4.0 in electronegativity. The species with the lowest electronegativities would be like cesium, you know, cesium or sodium. Cesium should have the lowest electronegativity. What's the electronegativity of cesium? It's like 0.7, 0.8. Actually, I don't remember. Roughly 0.7. You know. You check it. 0.7, 0.8. Sodium's like 0.9. So, you know, electronegativity, you know, the highest at 4, the lowest at 0.7. These are the Pauline's electronegativities. There are other scales in addition to Pauline's. But these are useful to know. Pauline's electronegativities. Pauline's electronegativities are just for the neutral elements. And so the biggest delta En, you know, the biggest delta En will be around what? 3, like 3, roughly. The smallest delta En will be what? 0. The smallest delta En will be between, like chlorine versus chlorine, they're going to have the same strength. So it's going to be a tie. Yeah. And so we're going to have a range of electronegativities that are going to vary from 0 to 3.3. Delta Ens vary from 0 to 3.3. You know what dictates quantum mechanics is a theory for the bonds. We aren't going to get into the mathematics of bonds or anything like that, but people do. Actually, we are. We're going to do some bonds in quantum mechanics, but we aren't going to do any hand calculations. We're going to do some computer calculations. And one of the calculations you can do is something called percent ionic character. You know, percent ionic character just means, you know, this. If it's nonpolar covalent, the percent ionic character is 0. If it's ionic, the percent ionic character is 100%. And so we go from sharing to winner takes all. And we're going to try to have some graduations in here because, you know, things will change. And so over here, with the biggest delta ENs, we call these ionic. And over here, you know, we call it nonpolar. And what we're going to see is we're going to see a range of values. And so if there's a slight difference, then we say it's just slightly polar. Because it's slightly polar, and then it becomes more and more polar, right? As we go along. And it's not linear, the trend. The trend is more like this. This trend is fitting a whole bunch of data. The data can be obtained experimentally. That is, you can determine the charge. You know the delta plus and delta minuses? You know, the dipole creates something called a dipole moment, and those dipole moments can be measured. So you can figure out what the amount of charge, the partial charge is on each atom. Or you can calculate those theoretically using quantum mechanics. But based on how much charge separation we have, we're going to have something like this. This is the trend line. This is the trend line. The trend line fits the data. The data lies like this. You know, there's some data that are outlier. If you look at this, you know, you look at the trend line and you look at the data, what do you think about the R squared, the value on this? R squared is good or bad? How about that? R squared good or bad? Bad. R squared isn't that great, you know, and so this is a crude correlation. R squared, not great. That means, you know, if you have an R squared that's not that great, there are other factors that are coming into play here. And so we're just looking at one of them, the delta EN, you know. That's it. But correlation is there. You know, it's not, this is, but correlation, we'll call it rough, is there. Somewhat rough. And so what we're going to do is divide it into 3 zones. So where should we make our dividing line? You know, because what we're going to do is, you know, these for sure are ionic, the ones with the highest percent ionic character, although they might not be 100% ionic, but it's close enough. These ones we're going to call polar covalent. And so where should we have the dividing line? The dividing lines are totally arbitrary. So for example, nonpolar, maybe this is nonpolar enough, even though it's slightly polar. And so we'll just say up to about 0.5, you know, delta here. And then maybe to about 2, you know, before it starts this, we call it around 2, we'll say it's polar covalent. But you know, it's arbitrary. How you set it. And so probably the best one is just percent ionic character, because that's much more quantitative. You know, but we'll just use this. You know, so typically a metal and a non-metal will form an ionic bond. You know, 2 non-metals that have difference in electron activity will form a polar covalent. And two nonmetals that are close in electronegativity will form a nonpolar bond. And so, for example, hydrogen's a little bit weird in the sense that, you know, where is its electronegativity? Because metals have a low electronegativity because more reducers. But does hydrogen have electronegativity that's low like the metals, or does hydrogen have electronegativity high like the halogens? Where is it? Is it low or is it high? Because hydrogen occurs in both group 1 and group 7. So is it on the left or is it on the right? Because that makes a difference. The highest electronegativity is fluorine. The lowest is cesium. So the periodic trend in electronegativity is electronegativity increases as you go right and up. The noble gases will have a very low electronegativity. We exclude those. And so where does hydrogen? Is hydrogen more electronegative than fluorine? No. It isn't. Hydrogen lies between boron and carbon, so it's halfway between the two. So hydrogen is at a 2.1 in electronegativity. Carbon's at a 2.5. And so if we have a carbon-hydrogen bond, like a hydrocarbon, hydrocarbons are nonpolar. They're called nonpolar because even though carbon is slightly more electronegative than hydrogen, the delta En is only 0.4 for a carbon-hydrogen bond. And so an example of this would be a carbon-hydrogen. Carbon's at a 2.5, hydrogen's at a 2.1, delta En is 0.4, which means we call it nonpolar because the dipole is so small, it's kind of negligible. You know, a very small dipole, delta minus, delta plus. It's not that significant. So we ignore it. Just call it nonpolar. All right, those are the types of bonds. And then not only do we have polarity of bonds, but we also have polarity for molecules. And so we have a bond dipole and a molecular dipole. The molecular dipole is equal to the sum over 3 dimensions of the bond dipole. And so here we'll have to know something about the structure of these. Let's just do some quick examples here. CO2, this is nonpolar. It's not because it doesn't have polar bonds. CO2 has polar bonds. There are 2 ways we represent the bond dipole in CO2. One, we could just put a delta plus here because carbon is less electronegative. And so what this means, delta plus and delta minus, is that oxygen's stronger in the tug of war, so oxygen's going to pull in more of the electron cloud and create a negative charge region here and a positive charge region here because of the deficit in electron density. We can also represent that with arrows. So the arrow always points to the more electronegative, and the positive tail points to the less electronegative element in the bond. And so these are the 2 ways, delta plus, delta minus, and the bond here. Dipole with the arrow. Well, if we look at the arrows here, we have 2 arrows equal and opposite, and so when we sum these 2 arrows, they cancel each other out. And so the bond dipoles are there, but the molecular dipole is 0. Equals 0 here. Another example would be something like this. We could have this is not a three-dimensional drawing, this would be a Lewis. And more properly, you do need a 3D drawing for this. You need 3D drawing. But this is a special case because you recognize this? What is this? That's kind of tricky. But there's 1, 2, 3, 4, 5, 6 carbon. 6 carbons is called hexane. It doesn't matter, you know, because the bonds, these single bonds are free to move. Because the molecule's moving about like this. But in something like hexane, is that polar or non-polar? You know, because the molecules are moving like this, well, the bond dipoles cancel each other out. And it turns out there are no bond dipoles. No bond dipoles. Or the bond dipole is negligible. There is a bond dipole, but it's so small. Bond dipole is negligible. Therefore, you know, when you sum up the bond dipoles, they're going to add up to 0. And so this is what we call a non-polar molecule. Non-polar molecules have no net molecular dipole. So CO2, is CO2 very soluble in water? No, it's not very soluble in water, bubble out of water. Because CO2 is what we call non-polar, water is what we call polar, and non-polar and polar don't like to mix, right? How about hexane? Is hexane very soluble in water? Not at all. Hexane is like oil, and oil and water don't mix. So, but what about CO2 in hexane? Will CO2 and dissolve in, hexane's a liquid, by the way. Will CO2 dissolve in hexane? Yes, it should dissolve pretty well because CO2 is nonpolar and hexane is nonpolar. And so for molecular compounds, we have the solubility rule, which is quite easy. For molecular compounds, the solubility rule is like dissolves like. How about CO2 and diamond? You know, CO2 is going to dissolve well in diamond. Diamond's nonpolar, CO2 is nonpolar, and do they dissolve in one another? And the answer is no, because like dissolves like is for molecular. Diamond is what? Network covalent. The network covalent is more complicated. We've got to look at it in more detail. And so, look at that. H2O obviously is going to be, you know, H2O. Let's do one more example. H2O is very common. H2O has this structure, which we call bent or angular. When you look at the bond dipoles here, the bond dipoles are going to point towards oxygen. Oxygen is more electronegative. And so we end up with a molecular dipole. So if this one's pushing this way, this one's pushing this way, we add the two together, the net molecular dipole is going to look like this. We'll be pushing this way. And this H2O is going to be a polar molecule. This will be the molecular dipole. All right, that's the bonds. There's some talk on bonds and types of compounds. Metallic bonds, like I said, we'll cover later. This is just polar, covalent and ionic. You know, and the only difference between covalent and ionic bonds is the degree of polarity. You know, with ionic means being most polar of the spectrum at one extreme. At the opposite extreme would be covalent. So this brings up this, you know, sometimes what we do is we assume, you know, all the bonds are going to be ionic or all the bonds are going to be covalent. You know? nonpolar covalent when we count electrons. When do we assume all the bonds are ionic when we're counting electrons? 100% ionic. You know, for example, water, I know water is not 100% ionic, you know, but water is fairly ionic because it's quite polar. The more polar it is, the more ionic, right? So water has a pretty high percent ionic character, but not extreme, you know, not like a salt, you know. But sometimes we assume that the bonds in water are 100% ionic when we do what? When we count electrons. When we count electrons by what method? Well, when we look at water, for sure, or even in CO2, you know, CO2, these aren't ionic bonds, but sometimes we'll assume they're ionic bonds to count the electron. Even in hexane, you know, hexane is much closer to nonpolar than it is to ionic. But we'll assume that these bonds are ionic when we're doing what? When we're determining oxidation states. Oxidation states, you assume it's 100% ionic bonding, even if it's not even close. Like here, hexane, it's not even close. This is more symmetric. And so what we say is nonpolar bonds have a symmetric electron clouds, like that. Whereas polar bonds have an asymmetric electron cloud like this. You know, asymmetric doesn't look even. You know, symmetric will look even. And so, even in something like hexane, we assume the bonding is ionic, right? Winner takes all. In this case, carbon's more electronegative, so winner takes all the electrons. But that's kind of far away from the actual reality. And so, how accurate are these, you know, oxidation states in predicting the properties? Well, as an actual charge, you know, it's not very accurate because the actual charge, if you look at the oxidation state for this carbon here, it's going to be 2, 4, 6, 7. It's going to be -3. As an actual charge, is this carbon actually -3 and these hydrogens +1? No. And so it's kind of far. The actual charge is closer to 0, right? And so, since we're so far off, does that mean that oxidation states aren't useful? They're in gross error? It turns out no, because, you know, when we count everything like that, this is why you can't compare the numbers. And somebody asked me about this, you know, you got a -2. Isn't a -2 for everything? No, it's not a -2 for everything because, you know, it's not an actual charge. You know, the only way it's useful is if you start memorizing what a -2 for this atom or this element means. That's the only way it's useful. And so you have to, because if it were an actual charge, then no problem. We could compare, because we compare a -2 on here, this carbon's -2, versus a -2 on this oxygen. Oh yeah, -2, -2, they're going to behave the same. But no, they aren't going to behave the same, right? They're going to behave the same. And so this is why oxidation states are a bit tricky, because oxidation states, you have to look, you know, it's a -2 on carbon. A -2 on carbon is totally different than a -2 on oxygen. Right? -2 on oxygen is much more accurate, right? The -2 on carbon, you can't compare the two. It's totally different. And not only that, they mean different things. A -2 on carbon means it's a great reducer. A -2 on oxygen doesn't mean it's a great reducer. And so those types of things you end up memorizing. Well, you're going to see, well, based when we start talking about polarity and charges and all this, you know, what exactly is this, you know? And so, you know, we have different ways of counting electrons. And so let's take a look at counting electrons. Let's just look at water. It's easy. we have oxidation state. Oxidation state, so I like to put, the oxidation state of hydrogen is +1. Oxidation state of oxygen is -2. Oxidation state of hydrogen is +1. So the oxidation states. Okay, what's another way of counting? The other way of counting is at the opposite extreme. What's the opposite extreme? Yeah, charge, but we have one more word, starts with an F before that. It's the blank charge, formal charge. The other way of counting electrons is by formal charge. With formal charge, what we do is, did I talk about formal charge yet? Not really. We assume that the bond is 100% covalent. When we assume it's 100% covalent, then everything's split 50-50. That is, okay, there are 2 electrons here, so 1 electron goes to that oxygen, 1 electron goes to the hydrogen, regardless of the difference in electronegativity. And so we just assume it. And so hydrogen ends up with 1 electron. How many valence electrons is it supposed to have? It's supposed to have 1 valence electron, so it ends up with 1, so therefore the formal charge is 0. You know, it neither has an excess of electrons nor deficit of electrons. It just has its normal valence. Oxygen ends up with 1, 2, 3, 4. These ones belong totally to oxygen, but these will split up, and so it gets 5, 6. So oxygen ends up with 6 electrons in the structure. Normally it has 6 valence electrons, so it broke even. So no extra, no deficit, so it's fine. This hydrogen is 0. So all the formal charges are 0. Now what is it? Is the charge on oxygen -2 or is the charge on oxygen 0? And the correct answer is it's neither. The charge on oxygen is somewhere between. It's between 0 and -2. Well, if it's between 0 and -2, what we call that is, we call it, somewhere between these two is going to be called delta minus. And the charge on hydrogen is going to be between 0 and 1, so that's called delta plus. And so a more accurate charge would be delta minus and delta plus, right? That would be a more accurate representation of the charge on each of those atoms based on the electronegativities. But what is delta plus? Do you know? We don't know, right? Is there a way to figure out delta plus? Tell me 2 ways you can figure out delta plus in delta minus. One way is you can experimentally measure the dipole moment. You can measure the dipole moment by the interaction of the molecules with an electric field. And from those measurements, then you can figure out what the charge separation must be, or what the dipole moment must be. The other way is you can calculate it. You can calculate it theoretically using quantum mechanics. Right? But are you going to do that for every single molecule? No. And so this is why we learn oxidation state. Oxidation state's super easy. Do you need quantum mechanics to calculate this? No. Do you need to set up some sophisticated experiment to measure dipole moments to determine that? No. So oxidation states are easy. You can do it on a piece of paper, back of envelope type of stuff. Formal charge, easy. And this is why we do formal charges. We compare formal charges with formal charges, and we compare oxidation states with oxidation states. They're easy to generate. And they mean something. If you do a little bit of memorization, they mean something. You can make predictions, right? Are you going to calculate or experimentally determine delta pluses and delta minuses? No, we aren't going to do that. Those are much harder. But we can still compare, because the larger the difference in electronegativity, the bigger the delta plus and delta minus is. You know, we can make some simple comparisons for delta plus and delta minus, because that makes a difference because sometimes oxidation states don't give us enough information. So for example, if we're comparing HF and HCl, which one's a bigger atom, HCl or HF? I mean, which one is chlorine or fluorine? Which one's bigger? Chlorine's much bigger. Chlorine's a lot bigger. But anyway, here, you know, we can make some predictions because when we look at the oxidation states, it doesn't give us enough information. You know, if I look at the oxidation states, this is +1, -1, +1, -1, no difference. If we look at formal charge, it's 0, 0, 0, 0. It tells us nothing. And so in this case, oxidation states and formal charge aren't that useful. And so what would be more useful is to try to make a prediction about, you know, which one's more accurate. And you know, sometimes oxidation states are fairly accurate. So for example, if you're looking at sodium chloride, oxidation states are fairly accurate because those are the actual charges. And so when you do the oxidation states for sodium chloride, you get +1 for sodium, -1 for chloride. Well, it is +1 for sodium and it is -1 for chloride, so that's very accurate. When you do formal charge for methane, you know, it's pretty accurate, you know. Or chlorine, it's very accurate. It's right on because if you're looking at Cl2, the formal charges are totally accurate, you know, as is oxidation state, but not for methane. And so for something like this, sometimes we try to make a prediction. We make a prediction like this is going to have a smaller delta minus, this is going to have a bigger delta minus because of electronegativity. Fluorine's most electronegative. If that has the biggest delta minus, you know, these have to be equal and opposite. Yeah. I mean, it's a neutral molecule. So all the deltas and all the formal charges and all the oxidation states have to add up to the net charge of the molecule itself. And so here, you know, in this case, it would be more, we could get more information from the delta plus and the delta minuses. And so what we do is for molecules, and we use all three. We use formal charge, we use oxidation states, and we use delta pluses and delta minuses to get as much information without having to do experiments and without having to do theoretical calculations. We try to get as much information about molecules as possible. Well, for Lewis structures, formal charge is going to be especially useful in Lewis structures, even though, you know, they don't seem that useful here. Yeah. Formal charge is the charge on the electrons, as is oxidation states. It's a charge on the electrons assuming you have covalent bonding. Oxidation states are the charge on the atoms, charge on the atoms assuming you have ionic bonds. And so let's look at formal charge in Lewis structures. Let's do something. You guys have done resonance forms too, is that right? Yeah. Okay, let's do something like this. We're going to do bicarbonate first, HCO3 minus. How many electrons do we have? Well, you know, hydrogen has 1 electron, carbon has 4 electrons, 3 oxygens, 3 times 6 is 18 electrons. Right. And then the charge, the -1 charge is 1 electron. And so altogether we're going to have 24 electrons. And then what we normally do is we try to come up with a skeleton, you know, H, C, O, 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 maybe something like this. But these types of links aren't good. You know, this type of link is called a peroxide link. Peroxide links aren't good. Oxygen doesn't like to bond to other oxygens unless it's double bonded. You know, this is okay. an oxygen-oxygen double bond, this is okay. But peroxide links are not good, weak, very weak. In fact, peroxide links, when you have a peroxide, visible light has enough energy to break it. And so if you have a bottle of hydrogen peroxide, it's got to be stored in a bottle that's not, in other words, it has to be stored in a bottle that's not going to allow visible light to hit the peroxide, because visible light will destroy the peroxide. And so it's normally stored in brown or amber bottles to block out visible light. And so we avoid these. We always avoid peroxide links. Well, a lot of people draw this structure. And this is probably because they like symmetry, and I like symmetry too. So this looks good, because it's all symmetric. And then we got 24 electrons. So the rule is you fill the octets to the outer electron. That rule, why do you fill the octets to the outer before the inner, atoms? Because normally we put the least electronegative in the middle and the more electronegatives in the outer. And that works. Yeah. But let's count the electrons. I have 8 times 3 is 24, 26 electrons. This is 26 electrons, which is too many electrons. Too many electrons. And so I have to get rid of 2 electrons. Let's get rid of 2. Normally I get rid of them in pairs because we like to pair things up. When we have single electrons are happy. Like for example, if I have a single electron here, something like this. A single electron, what that's called is called a dangling bond or a free radical. They're very reactive because they want to form another bond. So this would be a pretty good one. So we try to avoid that. Now I have 24 electrons. Does this structure look good? Did I count the electrons right? Let me make sure. I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 electrons. Does the structure look good? Did I miscount the electrons? It's okay. HCO3 minus. I must have miscounted electrons. I know I must have miscounted electrons. Because let's do the formal charges here. Formal charge on this oxygen is what? That's 2, 4, 6. And then we split this one in half, so it's 7. So the formal charge is minus. I circled the formal charges. This one's the same. This one's 2, 4, 5. This one's plus. This one's 1, 2, 3, 4. That's 0. Normally zeros we don't show. We just show the non-zero formal charges. But I'll write them here. There's some serious problems with this structure. Can you tell me what the problems with the structure are? Well, one, there's something called the octet rule. The oxygen, does it have an octet? No. So it has a partially filled valence shell. This isn't as stable as a filled valence shell. Filled valence shell would be an octet. Number 2, the charges, this charge arrangement looks terribly unstable. Why? The charge arrangement looks terribly unstable because one oxygen came out positive, that is, lost an electron. The other oxygen came out negative, it gained an electron. And so if you have a tug of war for an electron between 2 oxygens, which oxygen is going to win? Well, it should be a tie, right? Because they're both the same strength. And so this is not good. This formal charge arrangement is unstable. How can one oxygen taking an electron from another oxygen, basically. So that's not good. And so no matter what you do, how you change this, it's not going to work. So a nice symmetric drawing like this is not good. So we have to try a different skeleton. And the clue here is this. Bicarbonate's an acid. Acidic hydrogens are bonded to the most electronegative element. The most electronegative element. Why? When we think about acids, acids are H+. Bases have negative charge. And so acids are positive charge density, bases are negative charge density. And so the more positive the hydrogen is, the more acidic it is, the more susceptible by being attacked by bases like hydroxide. Hydroxide's negative charge density. And so this hydrogen, this would be a non-acidic. Because, when we have a hydrogen-carbon bond, that's pretty much a non-polar bond. Non-polar bond, like for example, is methane a good acid? I think methane's a good acid. Methane's an awful acid. Methane's the worst acid on your chart. The reason it's the worst acid is because the dipole on the hydrogen is so small. And so we have this situation. This is non-acidic. That would not be an acidic hydrogen. Hydrogens bonded to carbon are not acidic in general. Unless the carbon has an unusual charge on it. Yeah. If the carbon has a positive charge on it, it's called a carbocation, then it would be acidic. In general, not acidic. Unless carbon has an unusual charge. It'd have to have a plus charge on it. But it's possible it has a plus charge. When carbons have a plus charge, they're carbocations, they're called. There's a class of acids, they're called superacids. People are looking, actually at USC, this guy, Professor George Olah at USC won the Nobel Prize recently, not too many years ago. He was looking at these unusually reactive carbon-containing compounds because they have lots of applications. One of the applications is making synthetic gasoline mixtures. But there's lots of other applications. And so it's unusual for us, but not unusual for a person like George Olah. Deals with it all the time. Right? So we need to come up with a different skeleton. So the different skeleton we come up with is, it's better to bond this here. So we end up with a structure like this. Then we complete the octets. But we come up short. This would be come up too short. And so what we can do here, actually, no, we don't. I guess we come out all right. There it is. But this structure is not good because carbon doesn't have an octet. When the carbon doesn't have an octet, what we have to do is we have to make a multiple bond. So we'll take doesn't matter which oxygen, take a pair, drop it down there. But it turns out this oxygen still has a negative formal charge. Well, that's not bad because this whole thing is bicarbonate and it has to have a negative charge. And so the sum of the formal charges equals the net charge, which is -1 in this case. Resonance forms come about when we can rearrange the electrons. So for example, if this group of electrons pops in here and pops these out, then what we can do is we can generate the other resonance form here. We never move the atoms, we just rearrange the electrons. It does. And so we throw the double bond now up here. Took that group there. And create a single bond here. Turns out double bonds are shorter than single bonds. There's a negative charge there. For resonance, we show this with the double-headed arrow. That's to indicate resonance forms. Well, let's do that again. Let's take this pair and bring it down here and throw this pair out here. Okay. If we do that, then we can generate another resonance form, which is going to look like this. Okay, so when we look at the formal charges, this is negative, this oxygen becomes positive. How does that look to you? Does that look good? It doesn't look good to me. This one does not look good. Can you tell me why? Because one of the oxygens is positive, the other is negative. You got two oxygens fighting for electrons, which one's going to win? Is that stable? That one wins and the other doesn't? Although they're bonded differently, you know, this one doesn't look good. This one is not very stable. These two are equivalent in energy and much more stable. This one is not. And the reason it's not good is because of this. You're generating the formal charges. So when we have resonance forms, what's happening? A lot of people think resonance forms, then the negative charge, well, we'll eliminate this one. This one's eliminated. Eliminate this one, because this one is much less stable than these two. The high energy. When we have two resonance forms, are the double bonds resonating back and forth, and is the negative charge resonating back and forth? There's no resonating going on in resonance forms. What's really happening is what we have a hybrid structure. And the hybrid structure is a 50-50 mix in this case. It's going to be a 50-50 mix of the two structures. We don't count this third one. The third structure is too high in energy to be considered. Third structure, too high in energy. To be considered. And so we ignore what we call the contribution of that third structure. Now the hybrid is going to be a mix of the two. And so in the hybrid for bicarbonate looks like this. It's going to be a hydrogen with oxygen with carbon. And what we have here is that the double bonding electrons are going to be what we call spread out over this, both. And so basically it's this. We have something called the bond order. And so the bond order of this is 2, the bond order of this is 1. Single bonds are 1, double bonds are 2. The bond order for this is 1.5, so it's average of the two. It's not a single, it's not a double, it's a 1.5 bond. And the same thing with this. This is going to be a 1.5 bond. Here. The lone pair, you know, 2 lone pairs are fixed on each, but 1 lone pair is spread out between the two. And so the electron clouds spread out. And so this one gets a minus 1/2 charge here. This one gets a minus 1/2 charge. The net charge is still -1 because you add up the formal charges, sum them up to get the net charge on this. And so this would be the hybrid. This should be the most accurate. And the hybrid's based on the resonance forms that we generate. And so a -1 spread out over 2 atoms is going to average to -1/2, and a double bond spread out over 2 is going to average to 1.5 bonds on each. Okay. Now we're out of time, but we're going to do another example beginning class tomorrow, lab, nitrous oxide, which is a little bit more complicated than this.